All right, analysis of beams. Working stress design method. All right, so there is one method that is not really used that much anymore, but for the sake of learning it, because really the method is a method that can be used in any design aspect. For example, design of masonry structures, steel structures. So for learning the concept itself, I'm just gonna quickly review the method and get basically learn this. But this is not the method used anymore for concrete design. All right. So on this method, we are dealing with the allowable stress. We want to make sure that the stresses we are creating, it would be less than allowable stress, right? So do you remember the concept we have learned in your mechanics of materials? You would say the sigma, the actual sigma you're creating, right? It has to be less or equal to allowable stress that you have because of the material properties. This is because of what? The structure loading, right? All right. Your actual research to be less than allowable. Now this is a good design. So what we are doing is really just following this simple concept. All right. So let's look at this. For concrete and steel inside the concrete, we are going to have a limit. All right. I'm going to tell you why we are having a steel discussion here. Let me just tell you what's going on. First of all, this method is called allowable stress design, ASD. All right. Also, working stress design, it is called. Okay. So this is an old method used previously, but in recent years, it is not being used anymore in concrete, but in other structures, still it is being used. All right. This is the first thing. The second thing, why we are using the steel. If you remember, I said concrete, it is so on two main things, compression, tension, right? So how we have introduced this, we said F prime C for compression, tension FT. All right. What was our conclusion? We said FT is much smaller than F prime C. All right. So concrete under compression, good. It is a strong material. Under tension, it is weak. It is alarming. It is not good. If you remember, I said, all right, we're not gonna tension. We're not gonna basically assume it has any tensile strength, although it has a little bit, but we assume nothing, right? To compensate for this, to make up for this, for low tensile strength, we use steel in concrete. Why? Because steel has a high tensile strength. All right. So that is the reason concrete and steel, both of them are being considered at this point, because we are using steel inside concrete to compensate, to help for tension in concrete structures. All right. That's the term reinforced concrete created. Because we reinforce it with steel, reinforce concrete with steel. All right. So concrete in compression only use, right? Concrete only in compression, because we said, all right, nothing from concrete in tension. So this is your allowable. Right? 0.45 F prime, that's how much you're gonna go far. That's it. If you remember, you have seen this number. Where did you see this? If you remember, if I was talking about the stress strain diagram, I said, all right, 0.45 F prime C, if you go up, you're gonna reach to a point that you are at the linear portion. If you remember, that's how you estimate the modulus of elasticity of concrete. If you remember, I said, all right, that would be the point. All right. So this is F prime C on top, right? 0.45, which is here. This is the point you use for straight line, 0.45. Okay. So basically by making the allowable on this, you're working only on the linear region of the concrete. Okay. For a steel inside the concrete, depends on the grade 40 or 50 of a steel, you cannot go further than 20 psi, 20 ksi. If it is grade 60, you can go up to 24 ksi. These two are allowables as well. Depends on the grade. Depends on the grade. All right. So basically, what we're gonna do, we're gonna make sure that your concrete compression is less than this number. Your steel tension is less than this numbers. Depends on the grade of the steel you're using. All right. All right. So what is the procedure for WSD design? All right. First, determine the modular ratio, and this is from mechanics of, oh, this is from statics, as a matter of fact. Or let me think. Modular ratio for two different material in one section. No, it is mechanics of materials. Yeah. So if you remember, if you had like cross section made of two different materials, you need to convert the section to one material using the modular ratio. All right. So in this case, this is the modulus of elasticity of steel. All right. So modular of elasticity of a steel, 29,000 psi, 29 million or 20, well, this, it would be the same as if say 29,000 ksi, right? For a steel is that. For concrete, well, it can be different. It depends on F prime, so you can plug in for normal weight concrete. You can use this formula. We can find this. Locate the position of the neutral axis by summing first moment of the transform section about the neutral axis. Transform tension steel area by NAS. Basically, we're transforming. We're going to solve example. You're going to remember that. Transform compression steel. So we can have like a steel on top of the cross section. Using this, we need to transform it. And all right, so if we are working on the stress for the compression steel, we're going to work on this. If it is on deflection for compression steel, we're going to work with this. So by the way, the compression steel, it is not really common to include in our calculations, but to give you an insight about what we are talking about, right? This is a concrete cross section, right? This is a like something like this. It is a concrete cross section. Okay. So your cross section can be look like something like this. All right. I just want to give you introduction about different components of concrete cross section at this point because it is already named here. This is a rebar goes inside, right? Rebar goes all in, and the same thing here. All right. So these are our tension steel. Usually the one at the bottom, we're going to call it tension steel. The one on top, compression steel. We're going to talk about these all much more. So don't worry that how we understand the top or bottom, or it can be different. We're going to talk about all those. So one side, top or bottom compression, the other side would be tension if you have a steel. So you're going to name it like this. This is called a stirrup. Okay. Neutral axis of a cross section would be axis like this. All right. So if you remember from mechanics of material, one side would be under compression, the other side would be under tension. So in this example, the top side would be under compression, the bottom would be under tension. All right. That's how I named this steel. If you think about it, tension steel at the bottom, compression steel on top. All right. So that's why I brought this discussion to introduce different components you have in a cross section. All right. So tension steel is the bottom one here. Compression steel on top. Then we calculate the I, moment of inertia about neutral axis of the transform, and calculate actual stress and compare with the allowable stress. Okay. One thing before leaving here is that these two steel area, it shows by the area of a steel, A prime steel, right? The area of the tension steel is shown by the AS. All right, AS, the area of a steel on tension. A prime S, the area of a steel for compression. Cross-sectional area of tension steel. So I'm just going to say cross-sectional area of compression steel. All right. Okay. Let's go to the next slide. All right. So in order to basically compare the strength, the actual strength with the allowable strength for concrete, M times C, which is the distance of the farthest fiber away, if you remember, to the moment of inertia, is going to be your compressive, the bending stress, if you remember. So this is going to be your actual, right? This is your actual. This is your actual. For tension steel, just N multiply by MC over I. For compression, 2N multiplied by MC over I. All right. So having that said, let's look at this example here. Or we can pause it in here. Probably you're tired. It is. We have been in more than 50 minutes. So let's just pause in here and we're going to continue on the next video. Thank you.